Thanks everybody for having me out here. I don't know exactly how this is going to go, but there are certainly connections between what I'm doing and things Dana Scott did with denotational semantics that ought to be in your ballpark. And so let's see. So this is about a topic you don't encounter so much in the literature on intuitionism, but I think it's related. We're going to talk about scientific method and empirical simplicity. This is work with Kelly Genin, who's in the back corner there. And since you guys are mathematicians, you know what this means. That means there's no order. It's joint work. So Occam's razor. This is something mathematicians don't have to worry about, but empirical scientists do have to worry about it because empirical science is guesswork and you need some help when you're guessing. So the main thing scientists use to guess with is Occam's razor. So what scientists understand Occam's razor to say is when you choose a theory in response to the data, or you choose an explanation of the data, choose one that's no more complex than necessary. And then necessary means given the kind of data you have. So conclude the simplest theory possible, given what you've seen. So that occasions a couple of questions that have interested me for some time, and lots of other people too. First of all, what is this simplicity business? And second, even if you knew what it is, why should you rely on it to make guesses about the way nature is? Because the way I like to put it, sort of an updated version of the Meno paradox, if you already knew that that reality is simple, then you don't need an inductive method to choose. And if you didn't already know that reality is simple, then what business do you have presuming that it is? That seems to me to be a real problem. Okay, and then I just want to mention that Occam's razor is indispensable in science for a number of things. First of all, the choice of major theories has always been guided by it. Inductive inference in general, if you look at the philosophy of induction. Statistical model selection, so it's not just philosophers who talk about this, it's also statisticians. And in particular, my colleagues who do causal discovery from non-experimental data rely on it heavily. All right, so something you find in certain areas of machine learning and reasoning under uncertainty in artificial intelligence. In fact, I should mention, we just had Judea Pearl come out, and his speech to the whole computer science department was that machine learning foundations are not adequate for drawing causal inferences. That's exactly what this theory is aimed at. Okay, so he got the equivalent of the Nobel Prize in computer science to say that, and this is what he intended to be talking about to say that. Okay, so empirical problems. I'm going to start right out with the framework because you guys are the logicians. What's an empirical problem? It's a kind of a familiar thing. So let W be a set of possible worlds. Let's think of this as being sketched in possible world semantics. I is a set of propositional information states. And we're going to make two assumptions about I. The first is that it covers the set of possible worlds. That is to say, every world presents some information, possibly trivial. Right, so getting no information is to have an information state, the trivial one. That's what the first axiom says. So in a way, that's just not an assumption at all. The second is an assumption. We're going to assume that the information states are closed under finite conjunction. You can actually weaken that in a standard way, but it would take time to state it. And then what that means is information can accumulate. If you could have gotten this information, you could have gotten that information, then you could have gotten both informations. That's not always true, but by and large, I mean, statistics wouldn't work if something like it weren't true. And then a question. So there's a big literature in linguistics on questions, also in logic. And the sort of default view is that a question is a partition of the set of possible worlds into possible answers. Okay, so here's the space of possible worlds, and then the different colors are the different answers. That's a partition. And then the point of a question is that the interlocutor is supposed to help you locate yourself in one of the cells. Then an empirical problem is nothing at all except an information basis paired with a question. So you've got a set of possible worlds. Those are the possibilities you're worried about. You've got possible information states that you receive from nature, and then possible answers to a question, which is the information you're supposed to produce. So you can think actually of the question as output information, and the information space is input information. And inquiry is about moving from the input information to the output information, abstractly conceived. Okay, any questions so far about the framework? The ideas are supposed to be really simple in general, which it is. So when you have a problem and you get new information, so here's a new information state. I'm going to draw those as kind of like square, because square means simple and tractable. And then when we get an information state in a problem, the natural way to interpret getting that information is that it restricts the possibilities to the possibilities that are compatible with the information. And that's why we like information, because we don't like uncertainty, and uncertainty is possibilities. So information constrains possibilities is a common theme in philosophical logic, and it's just instinct in Bayesian statistics and probability theory more generally. You do this without thinking. But it's actually an operation, so we're going to draw it as an operation. There's the restriction. A relevant response given information E is just a disjunction of answers compatible with E. So if this is the original problem, instead of jumping up and down between the restricted problem and the original problem, we're just going to say a relevant response given that information to the original problem is a disjunction of answers compatible with that information, even though it's not cut down. Okay, that's just a convenience. Okay, so now we're going to start talking about topology. So I put this on this. I cut and pasted this off the web. When you say topology, you know, psychologists tell us that our ordinary concepts really are just exemplars and similarity. And so if you wanted to think of the exemplar of topology, I think most people conceive of this picture. In fact, it's all over the web, so that's good evidence of it. Sort of like the web is the collective id. And so the story is it's rubber geometry. But I don't want to think of it that way. What I want to do is to propose that topology is really something more general than geometry. It's the pure logic, or the pure mathematics of verification and verifiability. So if you're interested in verifiability, you're automatically interested in topology. And that's why topology is so useful. If I had time, I'd even argue that the applications to, and this is relevant, I think, to what you guys have been doing, that the applications of topology to geometry really can be subsumed under this idea of the mathematics of verification, because Hilbert, for example, in his paper on the infinite, talks about how the foundations of mathematics transform the infinitely small, which you can't conceive of, into the infinitely long. You can think of the infinitely long Dedekind cuts as data streams. You're investigating more and more of the expansion of a real number, and this fits with the Russian school of constructive mathematics, right? As to whether you can, what can you really know about? Can you know identities, or can you only know non-identities? That's exactly what's going on here. You can't know the exact identities. That's like an inductive hypothesis, and we'll see how that plays out later. I wish I could say more about that given the background, right? That's something I care about deeply. So let's see what I mean by that. W is an interior point of A, means W presents an information state that verifies A. By verifies, I just mean strictly implies. So strict implication is subset, right? So every possible world that makes this information state true makes A true, right? That's verification. And here's a world. So that world presents an information state that verifies A, right? So that's what an interior point is. An interior point is a world that affords information that verifies the proposition A. Maybe what I should say is that if you're just used to this as mathematics, propositions are here identified with sets of possible worlds. A proposition is either true or false. It's true or false in a world. Therefore, one can talk about the set of all worlds in which a proposition is true and identify the proposition with that set. So subsets of this problem space are propositions. A is a proposition. Information states are propositions. And what we have here is that W is a world that presents information that verifies proposition A. That's what it is to be an interior point of A. The interior of A, so interior is an operation on propositions, and it turns the proposition A into the proposition it will be verified that A. So you can really think of topological operations as modal operators. I think it's really cool, right? Because it transforms one proposition to another, and so you should ask yourself, well, what is the proposition that it turns it into? Well, so what interior of A is a set of all interior points. So that's the set of all worlds that afford information that verifies A. But if we assume that that information is coming in, then that's exactly the proposition that it will be verified that A. So let's think of where that would happen. Well, if I'm in the middle of A here, then yes, I'm going to get information that lands in the middle of A and verifies it. If I'm on the edge, if I'm in the boundary here, then always I'll pick up some points outside of A, so it will never be verified, right? So what is the interior of A? It's going to be this part, right? If this is A, that's the interior of A. It's the proposition that A will be verified. That's a way of thinking of interior. Then open sets are just the verifiable propositions. And what's a verifiable proposition? We say, well, it's a proposition that entails logically that it will be verified. So however A is true, you get information that verifies A. That's what a verifiable proposition is. All right, so in topology, that's the definition in terms of a topological basis of an open set. The open propositions are the ones that entail that they will be verified. That's a special kind of property of a proposition. The closure of A, so closure is a modal operator that takes A to the proposition that A will never be refuted. So of course, A will never be refuted if it's true. So any place it's purple is in the closure. But look, there are going to be other places where A is never refuted even though it's false, namely here. That's interesting, right? So in terms of scientific method, we're getting in the vicinity of Hume's problem of induction, because something can be true or false, but you'll never get information that verifies that fact, right? So that's the closure of A, right? So here's A, and then the closure of A adds the boundary in, because those are all places. If A is true, then of course it'll never be refuted. But if you're on the boundary where it's false, then still it will never be refuted. So that's added to the closure. And then closed is refutable. So A is closed if and only if the negation of A entails that A will be refuted. So that's closure. That's to be a closed set. So closed is refutable. Boundary of A says that A will never be decided. So one way or the other. Here it's true, but it's never verified. Here it's false, but it's never refuted. So both of those are in the boundary. Those are places where the question whether A is true will never be decided. So there's the boundary. Here's something a little less familiar, but it turns out to get a lot of play in semantics for provability logic, of all things. It's called the frontier. So the frontier of A is a modal operator that takes A to the proposition A is false but will never be refuted. So it disambiguates the two ways that the question can never be decided, right? It says you're in the boundary, but you're in the boundary on the not A side. Okay. So that's the frontier. See, only the dotted part gets in, so that's how it's different from the boundary. Locally closed. So this is a really interesting concept. So I actually rediscovered it, but it's standard and used a lot also in provability logic semantics, and also in algebraic geometry. So algebraic geometers talk about frontiers and local closure a lot, as we found out. I was sort of steadily reinventing a lot of that stuff from this Occam's razor application, which I think is kind of cool in itself. I didn't learn that stuff and then force it on the topic. It just was natural. So anyway, here's local closure. So A is locally closed if and only if A entails that A will become refutable. So A entails, so however A is true, you will get information such that in the restricted space to that information, A is closed. Like this. See, so if you were here, then you get this information state, and since there's no dotted line inside there, A is closed given that information. So here we are in the restricted space. If you're in the restricted space, it is closed. That's what local closure says. Now here's a cool thing about local closure. So you can think of this as a topological model for default reasoning. So think of E as being a default reason for A if and only if A is refutable but not refuted given E. Okay, so we think of proposition, right? So suppose that we have, well, let me put it this way. Yeah. Suppose that we have information such that when we get that information, the proposition becomes closed. Now we have a nice situation because if the proposition is false, we'll get a clean refutation of it. We won't be left in the ambiguous situation, right? So you're safe when you get that E to draw the provisional conclusion that A, because you know you'll be rescued if you were wrong. So you can think of E as a way of modeling what a reason is, an inductive reason. Yeah, okay. So let me just move on. So now empirical simplicity. So this is our target, right? All that other stuff is tactics for getting ready for this. Here's something that that actually Casey noticed, and it shocked me. There's a standard topological order called the specialization order. Now, the way I'm writing it is not exactly standard because we're doing it on sets rather than points, but it has a natural extension to sets. And so that order is A specializes B if and only if A is a subset of the closure of B. The usual one is done with singletons, right? So it's a special case. So in terms of our epistemological interpretation of things, let's see what that means. Well, that holds if and only if all information compatible with A is compatible with B. But if you contrapose that, it's all information refuting B also refutes A, which was exactly Karl Popper's definition of empirical simplicity. So Karl Popper was doing topology and didn't know it. So it's just contraposition. Right, see that? So this thing translates directly into this, and then this contraposes that. And then Popper put it as A is simpler than B if every potential falsifier of B is a potential falsifier of A. But that's just a way of saying all information states refuting B also refute A. Okay, so that was Popper's proposal for simplicity. We think it's a pretty good proposal, but not quite right. There are several standard objections to it and other objections we found. Here's one of them by this guy who some of you may recognize. Can you recognize? That's Clark Gleamore in his obnoxious youth. So he wrote a whole book working out this objection. The objection is that if I have a simple theory and I tack a bunch of horrible ad hoc auxiliary hypotheses to it, that doesn't make it simpler. That seems to make it more complex. But on Popper's proposal, it can only be as simple. It can't be more complex. That seems wrong. Okay, right? So adding, if you take a complex theory and add it to a simple theory, the thing doesn't become simpler. But on this proposal, it does. There are some other objections too. I don't have time to go through them all, but we respond with something very closely related that doesn't suffer from that objection. We call it this thing. So this is to signal to you that this is not always transitive. All right. So this is not even a pre-order in general, although in standard cases it always is. So it's A is simpler than B. So now it's strictly, it's not like a pre-order. If and only if A is included in the frontier of B, which means if and only if A entails that B is false but will never be refuted. Okay, this is a little different from specialization. Let's take a look at how it works. Well, it actually does just the right thing in standard cases. So here are some examples of particular problem spaces. Here, the worlds are infinite discrete sequences with discrete outcomes. So think of like green or blue as being discrete outcomes that you observe at sequential times. And you can think of those as being coded by natural numbers because natural numbers are discrete. So now you got infinite sequences of natural numbers. And then what will the information states be? Well, what do you see? The thing is, what do you think you would observe if the world is a sequence of observations? Well, by a given time, you'd observe some finite initial segment of those observations, right? So call that a cone. Now so the cone of worlds is going to be the set of all worlds compatible with that finite initial segment. So it's like it has a handle and then it branches out. So take the cones to be the observation states, the information states, and then you get an information basis. If you close that, you get a topology, which is the information topology. And then suppose that the proposition is you will always see green, right? Like all emeralds are green, if you know the philosophy literature. That would be just the singleton here on the bottom. And then the complement would be everything else that branches off. In that case, what you get is that all of them are green, is closed and refutable. The complement, not always green, is open and verifiable. And the sharp refutable hypothesis is simpler than the diffuse alternative, which is only verifiable. So this picks up on the intuition that sharp regularities are simpler than diffuse alternatives. If you think about in statistics, the point null hypothesis is usually favored by statisticians over the diffuse alternative, complex alternative. For us, that's going to be an instance of simplicity in Occam's razor. Continuous laws, this is another example. Here we've got that the worlds are functions in some class, say polynomials. You get finitely many inexact measurements along the function of x and y, so that's going to give you finitely many open rectangles. The information state corresponding to those observations will be the set of all functions in the class that touch every one of the rectangles, right? So those are going to be the worlds compatible with that. If the hypothesis is some particular function is the true law, then again, that's going to be closed. The complement will be open, and the sharp hypothesis that posits the law will be simpler than the alternative. I like this one. So Sierpinski space is the simplest non-trivial topological space. It consists of 2 points. The upper point here is that singleton is open. The bottom singleton is properly closed, right? And that's it. So you can survey the whole space. So this is the simplest space where you get a properly closed and a properly open set. And then I like to interpret this as follows. So a scientist, a senior scientist, of course, has a lot of graduate students to do all the real work. So she goes to sleep. She has herself put in suspended animation until something goes wrong with her pet theory. And then the students will wake her up at that time. So she goes to bed happy and complacent, and then if she never gets awakened, it's paradise. And if she does get awakened, she knows instantly her theory got into trouble, right? So the only two information states there are no awakening and awakening. And notice that in a certain sense, this compresses the previous examples down to their fundamentals. I can't get into it, but this is actually a topological quotient of those problem spaces with respect to the question asked. And so you can think of topological quotient as a way of abstracting from irrelevant information in a scientific problem. It's a really kind of interesting way to think about things. You can generalize this with multiple alarms. Then what you get is the bottom one is closed. Here, there's going to be no top one because there could be any number of alarms. All those guys are locally closed, and more numbers of alarms get more complex according to our simplicity concept. So more surprises, more surprising breaks in the future turn out to be more complex. That's the intuition. Euclidean metric topology. So we could think of there as being free parameters in theories that are real valued. That's how scientists typically think of complexity. So here's 0 free parameters, 1 free parameter, 2 free parameters. As you move up in numbers of parameters, you go from the bottom one being closed or refutable. The others are all locally closed, but not closed or open, so not verifiable or refutable. And the simplicity relation is exactly what everybody would say: more free parameters are more complex. That's all topology. I think we have to move on. So you get the idea with the examples. So the next thing is inductive methods. So this is going to be the scary part for you guys who like logic. All right, I'm warning you. This is empirical science. It's the dirty thing that other people in the university do. So reasoning. So there's this wonderful deductive reasoning, which my wonderful logicians like to talk about. And one of its properties is that it's monotonic. So you add more premises, you get more conclusions. You never get fewer conclusions when you add more premises. That's also true in intuitionism. Inductive reasoning is non-monotonic. So there's no steady foundation there. I love this image. So this is exactly how I think about empirical science. If you think you're getting more, you're kidding yourself. Okay, so here's a problem space, and here's input information. So inductive inference, we're going to think of as drawing a conclusion that's much stronger than the data, right? So if you're ever going to conclude that a model with 0 parameters is true, you have to be doing this. Whenever you choose a scientific theory and you don't have infinitely many terms on it, you're doing inductive inference. So an inductive method maps information states to conclusions that might be much stronger than the information state. Okay, so it's just a black box that takes information states to conclusions or answers, disjunctions of answers possibly, that are stronger. We say that such a method solves the problem in the limit just in case each world presents information such that M produces the true answer in W on any further information in W. For you guys, I should have just written it out in first order logic. For philosophers, this is usually better, right? So in every world, it eventually gets the right answer and sticks with it. So here's a picture of that, right? Here's initial information state. It's now saying origin. On any further information, it continues to say origin. So it's stabilized to the right answer. Okay, Occam's razor. So we have a lot of bases to cover here. Now we're on to the next one. What is Occam's razor? So I just said what simplicity is and gave examples, but Occam's razor is another thing. It says choose the simplest hypothesis compatible with the data or something like that. You would think that's an easy thing to figure out, but it turned out that that was harder to figure out than we thought. So it's something like output the simplest relevant response given E. Now, that almost sounds like just what everybody would say, but it turns out that you have to think about it. We're saying a simplest relevant response. That could be an arbitrarily weak disjunction. We're not saying a simplest answer. It's not science that before I've seen any data at all, I have to draw a strong conclusion, right? I might suspend judgment completely for a while and then wait until I feel confident before I make a strong conclusion. That's compatible with this version of Occam's razor. To say it's the simplest answer compatible with the data, we call gonzo Occam's razor, and we don't recommend that. Here's a related principle, Popper's razor, which is output a relevant response that's refutable given E. So sharply testable or falsifiable. And here's another thing. I don't have a person's picture to hang this on, but it's err on the side of simplicity. So in an arbitrary world, never produce a relevant response such that the true answer is strictly simpler than that response. But doesn't that sound, have kind of a nice ring to it? So, err on the side of simplicity. And then here's a surprising proposition. You don't have to choose between those because they're all equivalent. So those are exactly the same principle. And it's really not that hard to show either. It's just something that you don't, it's not the kind of thing that philosophers of science think of, right? It's not even the kind of thing that you would ask that these things are equivalent. So it was kind of surprising to us. And then this is topology. Patience is a related principle. It says never, the basic idea is never rule out a simplest relevant response given the information, right? So Occam's razor just says choose a simplest relevant response, but in a partial order, there could be many, right? So that allows you to plump for one of them. Patience says don't plump for one, wait for nature to weed down the field, which you can, given the definition of simplicity, that's always possible. And then this is independent of Occam's razor because Occam's razor actually says in the simplicity ordering, disjoin hypotheses that are closed downward in the order, right? That don't leave gaps. Even if there's an infinite descending chain, it's like you've got to fill the bottom of the infinite descending chain. Patience says it's like a dual thing. You've got to have spread in your hypothesis. You can't leave any chain uncovered. So it turns out to be co-initiality, right? You should disjoin answers that are co-initial with respect to the simplicity order. So this is patient but not Occam because it has gaps, but it's co-initial. This is Occam but not patient because it plumped for something simple. Here's a related principle. An arbitrary world W never output a relevant response that rules out all answers as simple as the true answer. And then those are equivalent. These are equivalent the way Occam's razor is equivalent to err on the side of simplicity. This says don't err on the side of complexity. So you can see there's a close relationship between err on the side of simplicity and don't err on the side of complexity. They're not equivalent, but they kind of cover the same bases. So Occam's razor justified. This is, remember there were two questions. What is simplicity in Occam's razor, which I answered topologically in half an hour. The next question is, why should you follow it? Why should you rely on this bias towards simplicity when you don't know what the truth is? So we're going to try to very quickly give an idea of how that works. So here's two notions of reliability. Deductive reliability is that you converge the truth directly. You never have to change your mind. This is tied to monotonicity. You'll never get new information that makes you drop what you said before, right? So it's like a straight path to the truth. That's why everybody loves deduction, and I do too, when it works, on intelligence tests and stuff like that. When you're dealing with the world, it doesn't work. Then life is like this. So a standard notion of inductive reliability is converge to the truth indirectly, which is what we already defined, right? That's convergence to the truth in the limit, which is often possible when deductive inference is not possible. Okay, so here's the thing. This arbitrarily crooked thing doesn't nail down any principles in the short run, because any convergent sequence is compatible with sticking in some other finite sequence at the beginning and still converges, right? So convergence limit doesn't mandate any methodological principles in the short run. It's toothless. That's a standard objection to the philosophy of science to talking about convergence. Whereas everybody since Hume has known, actually since Sextus Empiricus has known, that when you're talking about universal theories, you can't have deductive solutions to those problems because the data doesn't determine what's true. So what we think is, hey, there must be a Goldilocks sweet spot between these two, something that's not as weak as convergence in the limit and not as strong as going straight to the truth. It should be the criterion of success that's just right. And what we propose is, see, look at this road. This road is crooked, but it's not crazy like this one. This one actually is photoshopped, I can tell, because there's no such thing as this road, right? It's too stupid. But this is a true picture because this is not a stupid road. And why is that? It's because it goes as straight as it can, right? It goes as straight as it can. So how about, instead of saying either arbitrarily crooked or perfectly straight, couldn't be straighter is what we're after in inductive inference. It's like, be as monotonic as you can be when you can't be monotonic. It's an obvious idea. Optimize monotonicity. And our thesis is that Occam's razor is necessary for straightest convergence to the truth. So that's what's good about Occam's razor and nothing more. We have some ancient support for this. I like to collect this kind of support. So Sophocles says, do not fear for me, make straight your own path to destiny. And then the Lord will make your path straight. Allah will guide you to the straight path. And my favorite of all is the Katha Upanishad, which is fools dwelling in darkness, but thinking themselves wise, go round and round by tortuous, that is crooked paths. Notice, round and by crooked paths. That's going to be important in just a second. Because here's two ways to depart from straightness. This is a tortuous path, and this one goes round and round. And nobody would say either one is straight. Right? So there's some basic philosophy inspired by 600 BC texts. Right? We want to say this is constitutive of truth conduciveness. If you want to talk about a non-monotonic procedure arriving at or finding the truth for you, being conducive for arriving at the truth, then you're already beyond the straight path. So why not explicate it in terms of avoiding this as much as possible? Avoid this as much as possible. So here we're going to formalize this epistemically, a finite sequence of relevant responses in which every entry contradicts its predecessor is a doxastic reversal sequence. Doxastic just means about belief, right? So a belief reversal sequence is a sequence of outputs of the method, each of which contradicts the predecessor. It repudiates what you said earlier. You didn't just change your mind, you contradicted what you said earlier, right? So that's momentous. And a doxastic cycle sequence is just a doxastic reversal sequence where the last thing entails the first. So you went in a circle. That's a cycle. So now we've got doxastic versions of the tortuous path and the cycle, chasing your tail. Okay, and then simplifying a bit for time, solution M is reversal optimal if and only if every solution can be forced to produce each reversal sequence produced by that method, right? So if I produce only reversal sequences that every solution that converges the truth would produce, then I can't be blamed for my reversal sequences because everybody does it. Let me say that again because it's important. So take all of the methods that converge to the truth at all, that do arbitrarily many reversals, right? If my reversal sequences are performed by all of them, then I can't be blamed for mine because mine are necessary for finding the truth. If you complain to me about my non-monotonicity, I will say, look, it's necessary to perform those reversals if I'm going to find the truth at all. So that was actually a feature of my truth conduciveness, not an error. But if I do extra ones, then you can blame me for that. that make sense? That's sort of the main idea. Philosophers come up to us and say, well, isn't correcting your past errors a sign that you're doing well? And we say, absolutely. But doing extra ones is not a sign that you're doing well. You should avoid them. It's like a cost in computer science. If you're an inductive method, this is like a measure of loss, like Turing time. So why not minimize it, right? We're just taking the usual theoretical computer science attitude towards computation and applying it to inductive methodology, which seems to be a completely different area. And then you can do the same with cycles. So solution M is cycle optimal if and only if every solution can be forced to produce each cycle sequence produced by M. The same story. All right, so here's a result by our competing group in Amsterdam, Baltag, Gerashimchuk, and Sonia Smets. This is a real piece of topology. It involves concepts from algebraic geometry. So every solvable problem is refinable to a problem with a cycle-free solution. So by refinable, I mean the question asks at least as much. So if you solve this problem, you'd ipso facto solve the original, right? Because the question asks at least as much. So what this says is that essentially every solvable problem in the limit, right? Every problem that's solvable in the limit has a cycle-free solution. So to be cycle efficient, you have to produce no cycles, right? That's the way, essentially, up to solvability. So if you don't want the cycle, then you've got to do Occam's razor. Well, that's the next thing, right? Every cycle-free solution satisfies Occam's razor, and since you can be cycle-free by refining the question, that means that no cycles implies Occam's razor. So being cycle-free, which you could have done by refining the question and choosing your method appropriately, implies that you're following Occam's razor at every stage. Get it? It's necessary. So Occam's razor is necessary for avoiding the cycles. It's not sufficient. That would just be one way to skin the cat, right? If you go back and read your Kant, for Kant, the transcendental deduction is to show that something is necessary for having knowledge, not showing that it's sufficient. So this is not just one kind of way to find the truth. This is the only way to find the truth in a cycle-free way. What's the idea? The idea is very simple, actually. So here's, let's say, green is one answer, purple is another answer, and blue is another answer. All right? Now we get this information state, which is compatible with green. In this situation, our simplicity order is that green is simpler than purple. Why? Because green is a subset of the frontier of purple, which is how we define simplicity. Why? Because purple is false where the green is, of course, but it's never refuted where the green is, right? So that means that everything in green is included in the frontier of purple. All together there? So there's a lot of stuff to remember. So now here's the thing. This method violates Occam's razor because it says purple, which is more complex than green. Right? So he just violated Occam's razor because if he said anything, it should have been green or purple, or green or purple or blue, but it shouldn't have said purple because green is simpler and it's compatible with the information state. Now what's going to happen is, because this method solves the problem in the limit, given that it's a solution at all, there has to be an information state that witnesses its convergence to green when green is true. So choose a world in green that's compatible with the information so far. There's going to be an information state on which the method now says green because it's converged to the truth. But of course, we're on the boundary of purple, so there's got to exist by the definition of boundary, there has to exist a world in purple that's compatible with the data presented so far. And in that world, because this is a solution, there has to be an information state around that world on which the method converges to purple. So we just forced the method who violated Occam's razor to perform a cycle in belief. Okay, so violating Occam's razor easily implies that you can be forced to produce a cycle in belief, a doxastic cycle. And that's all topology. Main result 3. I'm not even going to state this. This is a really nice piece of work that Casey did. I think it's fundamental. We can give a characterization of the solvable problems that have reversal optimal solutions. Right, so you can characterize that, but we wouldn't want to say that every solvable problem essentially has such a solution. In fact, we have negative results that are very strong against every solvable problem, even having a plausible variant that has a reversal optimal solution. But, you know, if you do have a reversal optimal solution, you should use one. Right? So it's not a problem that there are some problems where there isn't one. If there is one, you should use it, because we have exactly the same attitude towards deduction. If deductive methods work, you should use them. That doesn't mean that deduction is bad or should never be used, because it doesn't always work. If you're on an intelligence test, use it. Main result 4. A solution is reversal optimal only if it's patient. Okay, so here's the take-home message. Occam's razor is necessary for avoiding cycles in belief, and patience is necessary for avoiding unnecessary reversals of belief. So the Upanishad was very deep because it mentioned both the cycles and the reversals, and each one characterizes a different aspect of Occam's razor. It factors beautifully into the 2 losses. So this was kind of stunning to me, because I was walking in the wilderness for 15 years on this, and without separating those principles, it's a mess. So there's something, I think, deep and mathematical about focusing on the 2 as separate losses. I just want to show you one more thing. So Occam's statistical razor. So now Occam is playing with dice there. The next message is, in real science, every theory is stochastic, at least due to measurement error. Okay, so even if you are a dyed-in-the-wool deterministic Newtonian, when you measure altitude and azimuth of planetary positions, you do it with a Gaussian error model because of stray causes of observational error. So essentially, every theory is stochastic, which means probabilistic. And then that's different because you get a random sample. You don't get this determinate logical information packet, which we've been assuming up till now, right? And for philosophers, that's a big deal because they say, where does this true information come from? All we see in science are these scatter plots. So we need to connect the whole topological story to statistics, or it's not going to be a real foundation for science. I like this one. So this is not Star Wars. Notice this is Stats Wars. So stats is short for statistics. There are 2 schools. This may not interest you guys so much as many in this university, but believe me, it interests a lot of people. That there are 2 schools of statistics, the Bayesian and the frequentist. And from our point of view, the striking thing is that the Bayesians allow you to do any kind of inductive inference, but they don't give you a theory of why you're getting to the truth when you do that. They call it coherence, and then that's a totally different thing from reliability or finding the truth. It's just a way of managing your opinions. Don't ask why they're true. Just believe them. Whereas the frequentists don't allow you to do any inductive inference, but everything they say is based on reliability or bounding chances of error. So it's curious to me that you have this flip, right? You can either be an inductive skeptic and talk about reliability, or you can just open the floodgates to induction but have no reliability story at all. And guess what? Nobody's happy with either, not surprisingly. Okay, so what we want to propose is that using our topological approach, we can make everybody happy by giving you a theory of statistical induction that's based on a concept of reliability. Okay, so that's the big aim. And the short story is that the preceding concepts and results, after a long time of working on it, now appear to extend almost effortlessly to statistical inference. Big story. Nobody knows that story yet, but it's a big story. So we're proposing that this is a new foundation for frequentist statistics that is not a replacement for what they had. It's an extension to terrain that they can't even talk about because they don't allow for inductive inference. And Bayesians do. So here's a basic recipe for how to do it. Not every T is crossed here because we don't have time, but this will give you an idea of how it's going. So W now is not a set of these point possible worlds. It's going to be a set of joint probability distributions over some set of variables, just the way statisticians set it up. And this X vector sub n is going to be a random sample of size n of those variables. That's just completely standard. And then a method is really going to be a method for every sample size. And then at sample size n, the method is a measurable function of the sample space that's almost surely continuous. The chance of landing on the boundary of a zone is 0 for every probability distribution in the set. See, when you're doing statistics, you look at, does the sample fall in some rejection zone or acceptance zone? Nobody cares about what happens on the boundary of those zones, right? We're talking about, it's an idealization that you're getting real value measurements at all because everybody records their data with 4 decimal points, right? So you're not really getting points in Euclidean space. You don't want to overwork that idealization by saying, I really care about what happens when the sample point hits a boundary. The crucial thing here is the information topology. There are no information states, and that's what generated our topology, right? So there's a gap. But here's a way to think about it. A statistical method draws conclusions based on whether a sample point hits an open region of sample space, right? We only care about the open regions. And 2 distributions are less distinguishable if they produce smaller differences in the chance that such a region is hit. Right, you're using these regions as a way to make statistical decisions, right? So when distributions get close, it's hard to use a rejection zone to separate the 2 distributions. This is just standard sampling theory. So the information topology should be a topology that judges distributions as close if it's hard to tell them apart with those kind of procedures, right? And so for you guys, I can say, it's the final topology for this collection of maps, which means the course's topology that makes all of those maps continuous. That's a nice categorical way to define what the topology is. And it doesn't include anything more than what we need. So we believe in being minimalist in terms of just getting the epistemology to work without adding a lot of bells and whistles. So what are these maps? See, this is a map from distributions to chances. So the range is the 0-1 interval of probabilities, and the domain is the set of all possible worlds. And then they're parameterized by what the open acceptance zones are and what the sample size is. So you throw in all of those and then make all of those maps continuous, and you get the information topology. Then simplicity is exactly what it was before because it's topological. So everything we define in terms of topology now carries over with the information topology. And then for the methodological concepts that involve the statistical method, we have a standard way of dealing with them. Just repeat what we said before topologically, but add in chance. Make them all hold in chance. So convergence to the truth becomes convergence in chance or convergence in probability, straight out of your textbook. A reversal sequence becomes an alpha reversal sequence. What that means is you produce, I think I've got a slide on that. So Occam's razor becomes Occam's alpha razor, patience becomes alpha patience. And let me explain what those alpha things mean. So, you know, in frequentist statistics, those would be significance levels, right? They would be bounds on the chance of type 1 error. With inductive inference, you can't bound anything, so you can't have that. But you can have something that looks just like it. Here's an example. Again, we're going to have a 2-parameter space, but here these are statistical parameters. So worlds are bivariate independent normal distributions. And the question is, actually, I want to strike the independent. I changed the picture. So they could be dependent. The question is, which mean components are non-zero? So let's say the covariance is fixed. The mean components are not fixed. So we get 2 parameters, one for each mean. Then if you look at the sample space, it looks just the same. That's X bar, Y bar space. So those are the sample means. And then the footprint of, say, this distribution will look like an oval that reflects the covariance. And then a method is going to partition the sample space into regions corresponding to answers. So this one says the origin, if you're in this oval, if the sample lands in this oval. This says axis if you land in the green area, etc. Sector if you land in the blue area. So this is what a statistical method looks like. A reversal sequence is just what it was before. And now we say M produces the sequence with chance greater than or equal to alpha if and only if the chance that the method produces that each successive answer at each successive sample size is greater than alpha, right? So this is an existential quantifier. So you say if there exists sample sizes, a sequence of sample sizes that are increasing, and there exists a world such that the chance that that world and those sample sizes of the method saying the successive reversing answers is greater than or equal to alpha, then the method has produced that sequence with chance at least alpha. That's not significance at all. This is about a tolerance on how much reversal and chance you want your method to be allowed to have. It's like a tolerance on reversals and chance. Reversal efficiency is that you only alpha produce cycles or reversals that every convergent solution in chance can be forced to produce. And let me cut to the chase here. Okay, well, Occam's razor is don't have chance more than alpha of violating the err on the side of simplicity principle, which is defined pointwise. I know this is going a little fast. You can also do alpha patience, which is don't violate the pointwise version of patience with chance more than alpha. That's why we do the pointwise versions of the 2 principles. It makes this really painless. And the main result, which is what I'm racing towards, is every alpha cycle-free solution in chance to a statistical problem satisfies Occam's alpha razor. That's an exact analog parameterized by alpha of what we did topologically. Exact analog is complete success. And this is not significant. So if you read in the newspaper all this stuff that statisticians say don't report p-values anymore, we're not. This is something new. It looks like a p-value when you apply it to designing methods, but it's not. And conjecture, which this guy claims he got over the break, is that every alpha reversal efficient solution satisfies alpha patience, which would be the exact analog of the other complementary result. And we have simulations of how these things work if you want to see statistical simulations, but I think I want to stop here so there can be a few questions.